So we're on page 25 in your workbooks, and we'll be looking at arithmetic growth and decay. And so what we're looking at with arithmetic growth and decay is essentially just an application of what we've seen with arithmetic sequences. So let's take a look at that very first class example then. So reading that through, it says BP Birthplace Forest Program in Calgary enables parents to honor their children by planting a tree when their child is born. At the same time, shows concern for our urban environment by encouraging the growth of city forests. Some of the trees planted have been growing at an average rate of 12 to 18 inches per year, and the program was launched in the year 2000. So what we're going to look at is two students, Joel and Jenna, and how they've interpreted this problem in terms of how they're going to solve it. And so that's the most confusing part probably with this particular application, is deciding how it is that you're going to take the information and construct your sequence. So if we take a look, the evergreen tree is 6 inches high, planted in June of 2000, and having a growth rate of 15 inches per year. So we've got Joel, two students then are asked to determine the height of the tree in June 2011. And so you've got Joel, who forms an arithmetic sequence with 6, 21, and 36. Jenna forms an arithmetic sequence, and hers is 21, 36, 51. And so using the formulas in the previous lesson to determine each student's answer to the problem. So before we go ahead and do that, let's just take a look once again. So we've got Joel, and Joel's sequence is 6, 21, 36. And so what are we seeing right here is, so he's saying in June 2000, so we'll say that this is the year, and he's got term 1 as being 6. In 2001, he's saying that that's term 2, and the height is 21 inches. In 2002, then n is 3, our third term is 36. So if we take a look at that in 2011, we are trying to figure out what the height is going to be. And so what is our n value? Well, often something that I would recommend that you guys look to do is to make a 3-column table even, matching up. If the year comes into play, for example, how does that correspond to our n value? So we might be able to see that our n value in this particular case is always going to be one more than the year. So 2000 what then? In which case we are looking, Joel will be looking for term 12. And so the height will be term 12. On the other hand, we've got Jenna, and Jenna's, let's see if I can squeeze that in here. Jenna has her sequence, and it looks like 21, 36, 51, and on from there. So if you take a look at Jenna's, her year, if she says her very first term for her height is 21, and that's after the first year. So she's got 2001, and 2002 then is when we're looking at the second term number, or the second year, and we're looking at 36 inches in height. 51 inches in height is then after the third year, or in 2003. So when we're talking about 2011 for Jenna, her term number, that is after the 11th year, and so we're looking at term 11. So if we take a look then, and we answer this question using the formulas in the previous lesson. So we've got, switch back to blue for Joel. So for Joel, he's got A is 6, and our common difference is 15, and in his particular case, n is going to be 12. So looking for June 2011, we are looking at term 12. And so we have A plus n minus 1 times D for term 12 is equal to 6 plus n is 12, so 12 minus 1, which is 11 times D, which is 15. And if we look at that, that will be 171 inches, assuming a constant height growth of 15 inches per year. If we take a look at Jenna's, then Jenna, her A value is going to be 21 inches. Common difference, we're still looking at a growth rate of 15 inches per year, and her N value is 11. So do we still end up with the same thing? So we're looking at term 11, and again, A plus n minus 1 D, and 21 plus n, which is 11 minus 1, or 10 D. Oh, sorry, we know what D is. D is 15. So 10 times 15, so 21 plus 150 is again 171 inches. So as expected, they are coming up with exactly the same answer of 171 inches for the height of the tree in June 2011. They're just doing it, going about it at a different in a different way, because Joel's sequence starts with 6, and because of that, his n value is 12, whereas Jenna starts with 21. She's starting with the growth rate after the first year, so A is 21, so n is equal to 11. Are we expecting that their general term formulas are going to be the same or different? Well, because we've got different A values, then those general terms should definitely be different. So let's take a look at Joel's. So Joel's is Tn is equal to A plus n minus 1 D for our general term sequence. We're leaving Tn as just general. A is 6. D is still 15, so distribute that 15 in. Tn is equal to 6 plus 15n minus 15. And so our general term formula is Tn is equal to 15n minus 9. So again, because this is arithmetic, it is also a linear function, so that it can be written in a form of y equals mx plus b. If we take a look at Jenna's, then again, Tn is equal to A plus n minus 1 D, and where her A is 21, but D remains the same at 15, so Tn equal to 21 plus 15n minus 15. So if we are using Jenna's, then Tn is equal to 15n plus 6. Okay. So explaining why the formulas in B and C are different, of course, we have different A values. So different A values. Okay. And also different N values. So if the tree continues to grow at the same rate, in which year will it reach a height of 28 feet? So again, depending on if we're referring to Joel or Jenna, so let's take a look. 28 feet, you guys know from, certainly from last year, but probably previous to that as well, that first thing that we need to do is change that into inches, because both general term formulas are looking at inches. So 28 feet is equal to 28 times 12, or 336 inches. So if we take a look at using Joel's formula, so for Joel, we've got Tn is equal to 15n minus 9, and Tn, so 336 is our Tn, so 15n minus 9 or 345. If I add 9 to both sides, is equal to 15n. So then n is equal to 23. On the other hand, if we've got Jenna's general term formula says Tn is equal to 15n plus 6, or 336 is equal to 15n plus 6. Subtract 6 from each side, so 330 is equal to 15n, and so n is equal to 22. So as expected, we should be expecting that we're getting different n values. They should both refer to the same year. So if we take a look at Jenna, so if I start with Jenna, for Jenna, n is equal to 1 in 2001. So when n is equal to 22, then it is in 2022. For Joel, let's switch back my colors. So for Joel, n is equal to 1 in the year 2000. So then that means that n is equal to 23 in 2022. So of course, should be the same. So in which year will it reach a height of 28 feet? So that will happen in the year of 2022. So it doesn't matter which method you are to follow, if you follow Joel's method or if you follow Jenna's method, but you don't have to do both, but you do have to pick one and pick the appropriate values. Okay, let's take a look at the next question. If you turn over the page onto page 26. So arithmetic decay, as you can imagine, that is when things are getting smaller. So that happens when we have depreciation, so losing value. So that frequent thing that people talk about, depreciation, would be the value of a vehicle. Other things that we buy, which people liked to have new, or they say that it works better when it's new and it loses value over time. And so an example that they're giving is a printing press. So if that's bought in the year 1992 and it depreciates in value by the same amount each year, 5 years after it was bought, the printing press had a value of $311,000 and a scrap value of $2,900 in the year 2010. So using an arithmetic sequence to determine the amount of annual depreciation. So again, up to you how you want to write out your arithmetic sequence, but I would always suggest writing that out. Again, you might have 3 columns or 3 rows to go through it. So let's take a look. If we know that it's purchased in 1992, then the value 1 year after, so 1992, we don't know. 1993 is 1 year after, so 1 year after, and we don't know its value there, but we know 5 years after that it was bought, it was worth, so 5 years after it was bought, and that is in 1997, and it had a value of $311,000, excuse me. And then if we take a look in 2010, the value was $2,900. And so how many years after it was purchased? 18 years after it was purchased. So what we can say then is this is going to be our N, and this will be our Tn. So Tn, we can say, is going to be the value of the press N years after 1992, meaning when it was purchased. So what is it that we know? We know that T5, 5 years after it was purchased, it's worth $311,000. Term 18, or 18 years after it was purchased, it's $2,900. So we can set up that system of equations. In this particular case, T5, n is of course 5, and T18, n is equal to 18. And so then we know that Tn is equal to a plus n minus 1d. So then 311,000 is equal to a, we don't know, plus n, so 5 minus 1 or 4d. We don't know what the depreciation is. That's our common difference. Similarly, 2,900 is equal to a plus 17d. So if we take a look at that system of equations and solve that, then we've got negative 13d here is equal to 308,100. Divide both sides by negative 13. So then our common difference is negative 23,700. So that is our annual depreciation. Okay, so it's going down in value every year. That's a lot of money. Is 23,700. But I don't have to write the negative when I write the depreciation because that assumes that actually indicates that it is going down. If we're looking at the purchase price, then we're looking at, well, we need to find A. So, but remembering that what is our A value? Our A value is going to be 1 year after the purchase. So if we take either of those, A plus 4D equals 311,000 or A plus 17D. So let's take that first one. We know 311,000 is equal to A plus 4D. And we now know what D is. So 311,000 is equal to A plus 4 times negative 23,700. So would you just hit pause and go through and solve and come back, and I'll do the same. So if we take a look then, going through and solving, so we distributed the 4 in, so A minus 94,800. So we end up with A is equal to $405,800. So remember, A is the same as term 1, and so that tells us that the value after the first year was $405,800. So therefore, to figure out the purchase price, we need to add on that depreciation, the amount that we lost. So adding back on another 23,700 gives us a purchase price of 429,500. Okay, let's take a look at the next page then. So again, relating our arithmetic sequences to linear functions. And I think you guys should be pretty good with this. So read through the instructions and complete the table as well as the graph. So hit pause, go for it, and once you've finished the table and the graph, you can come back and take a look at what I have as well. So the situation is a pile of bricks that have been arranged in rows where 28 bricks are in the first row, and the number of bricks in each subsequent row is 2 more than the previous row. So a nice recursive formula in words right there. Okay, so hit pause, and we'll reconvene in a couple of minutes then. Okay, so because we have the first 10 rows, so the row number they've called R in this particular case goes from 1 through 10. Number of bricks, of course, started with 28, and we're increasing by 2 each time. And then in every single case, you're graphing that. Should you be joining the points or not? No would be the correct answer, because the row number, we're looking at discrete values, and the row number is, of course, all natural numbers. So determine if the range is an arithmetic sequence, the range being the number of bricks. And so we can see that list 28, 30, 32, 34, and so on is obviously going to be an arithmetic sequence. So of course we can say yes. How do we define it as an arithmetic sequence? Because we have a common difference. So the common difference is 2. Okay, so the domain of the relationship is, of course, our R values. And so we can say, if you wanted to use set notation, we can do that. So it's a set of R values and such that R is an element of a set of natural numbers. If we wanted to be more specific, if we're only looking at what's happening in A and B, because it only goes between 1 and 10, then we can be more specific. So A, or in A and B, we see that it's a set of R values such that R is greater than or equal to 1 and less than or equal to 10, and R is element of set of natural numbers. So that's putting in the boundary points. At the same time, somebody might argue that we actually don't need to show this piece right here. We could potentially just say that it's a set of R values such that R is less than or equal to 10, and R is an element of a set of natural numbers, of course, that being because R is never going to go below 1. So it's always going to start at 1 as a natural number. So why does the graph not have an intercept on the vertical axis or your y-intercept? Is because there is no row 0. Okay, and write the equation for the number of bricks in a row, n as a function of the row number. So that, of course, is just simply going to be our general term formula. But keeping in mind that they've mixed things up a little bit, because normally instead of R, we would have n. Instead of n, we would have Tn. So let's just start with our general term formula, and then we'll put everything in from there. So Tn is equal to A plus n minus 1 times D, but instead of Tn, they actually have n, not confusing at all. A is 28, our first row has 28 bricks. Instead of using n here, we are looking at R minus 1, and the common difference is 2. So we're still going to clean that up. So n is equal to 28 plus 2R minus 2, or n is equal to 2R plus 26. Okay. Great. So would you please complete the homework? And I would like you to complete, so page 28 to 31, and I'm looking at basically everything except for number 4. So we'll go with 1, 2, 3, and 5 through 10.